All right, so part 3, we're going to talk about a paper that ties everything together. It goes back to chapter 2. Pepto-bismol is good for your stomach because it destroys bacteria in your stomach without destroying your stomach. And the reason why it does that is not because you are somehow immune to bismuth. Bismuth will affect you and will be just as toxic to you as it will be to bacteria. The reason is not thermodynamics. It's just as sticky. The reason is kinetics. It won't have a chance to get into your cells, and it won't have a chance to harm them. And that's really a chapter 6-7 concept. So that's what this paper is about. And they actually answered the question by using a complicated systems approach to metal-based pharmacology. This is just a question of you're looking at the whole system. How does bismuth work in Pepto-bismol? Here's the actual paper itself. Glutathione and multi-drug resistance protein transporter mediate a self-propelled disposal of bismuth in human cells. So you can see that somehow one of the advantages that you have is you have glutathione. You also have a multi-drug resistance protein transporter. That's great. But bacteria, don't they sometimes have some things that work like glutathione do, too? Is it possible that bacteria might be able to pick up on our tricks and develop resistance to bismuth? Well, the answer is actually no. But to understand why, we have to look at how it actually works. So it is like it says it's a systems approach, and it's the question of when you have bismuth getting into a system, you're flooding, when you drink Pepto-bismol, you're flooding your stomach with bismuth. And the bismuth actually goes, and it is able to get into your cells. It's sticky, and it sticks to stuff. And so you actually have these 4 different things that show 4 different metals, what happens to them. The bismuth, it should have been pink, honestly, but the bismuth is blue, okay? And so you see the bismuth is going into the cell here, and it's showing a eukaryotic cell. It's showing one of your cells, not the bacteria. And inside, you see you have GSH interacting with it and binding to it. So this follows the pattern that we set up in chapters 1 and 2. If you have something sticky entering the cell, you make a thiol-containing, sulfur-containing molecule that you can stick to it and throw it away. It's like fly paper, okay? So what happens then is that then the bismuth sticks to the sulfur. The bismuth moves through this MRP, which is multi-drug resistance protein. Basically, it's there to look for glutathione stuck to stuff and to put it into places. It either throws it outside directly here, or it puts it into little vesicles that then it can store away where they're away from anything. The important thing is to get it out of the cytoplasm. And again, the cytoplasm, by the way, is reducing. Therefore, your thiols are SH, not SS, and they are ready to react with bismuth. So that's the main thing that they found here. They found that glutathione works this way. The different metals work in different ways, but you see that glutathione is actually involved with all of them. Here's gold up here, here's platinum down here, or actually copper, I'm sorry. Platinum actually works in similar ways. Gold, copper, and even arsenic are all detoxified by glutathione-related mechanisms, and eventually you get it out of the cell. So this is cool. Could bacteria develop a resistance? Could bacteria evolve a lot of glutathione and be able to get rid of it the same way that we do? And that's one of the questions that they were sort of asking. So when they looked they looked at cells, your cells, and how do they protect from bismuth? And there's 3 pathways that end up protecting them. This is a zoomed in version, the paper version of the blue stuff on the last slide. And so you see right here that you have the first order of defense is the membrane itself. Number 1 is bismuth has to get across the membrane and into the cell. It's not a specific transporter, it's just a passive transport kind of thing. It has to hop the fence. And of course, if it's at a high enough concentration, it can. When it gets inside, the glutathione can bind to it, and it can make this little bismuth bound to 3 glutathiones here, right there. And you see that once it's bound to glutathione, it can be stuffed into the organelle here, or it can be ejected. Both of those are mediated by the same MRP transport protein. So that's kind of cool. There's the question of when you have the glutathione being used, what does the cell do? The cell actually makes more glutathione. it detects it through this number 3 pathway, and it makes more GSS that then becomes GSH and is able to stick to more bismuth. And so you have 3 lines of defense, sort of. You have the fence, you have the glutathione itself, and you have the process to make more glutathione. Okay? And all of those can be turned on by bismuth. And what they were looking at is they were looking at which is the most important of these. You have all of these. Bacteria could evolve a number 2 or a number 3. Maybe they would have to eject it rather than make a vesicle, probably, although they can do some things like that. And so the question is, but number 1 is just sort of a physical phenomenon. It's not really a biochemical one. And so what they wanted to do is they wanted to look at the different points. And the way they looked at point number 1 is just actually a diffusion problem that could have been a homework problem that you were given by Atkins. I want you to see how they modeled it. They characterized passive transport, and they used, doesn't this look familiar? dj dt, dj at time t over dt equals proportionality constants times the difference in concentration at time t. The original concentration minus the concentration at time t. This looks like a chapter 6, chapter 7 type thing. And they even go through and they even integrate this. They go from here to here, S1 to S2, by integrating, and they end up even with an e to the negative x function. They end up doing a calculation for how much bismuth hops the fence. They actually do an integrated rate law. And because it's a simple kind of reaction, it's a simple calculation, and it looks like the same level, you are actually equipped to follow what they do in part 1 here. Because all it is it's an A to B reaction. A is concentration outside, B is concentration inside. How fast does it happen? So because it's an e to the negative x function, by the way, you're also familiar with the shape of these. It's going to be some kind of curved line with some kind of asymptote. Depending on how you look at it, it's either going to be a curved line down, outside, or it's going to be a curved line up, inside. And so they're looking at an intracellular level, so it's a curved line up. Over time, you have bismuth outside, it gets into the cell, and they were able to actually take this model, compare it to the actual data, and say, hey, those look exactly the same. So it looks like our model is collecting most of what's in the data. What's interesting is once you have the model, you can actually see what the model depends on. And you can calculate this model. Part of the reaction is the surface area of the fence that the bacterium has to jump to get inside the cell. So the intracellular volume is related to the surface area, and the surface area is the limiting factor. It's the energy that the bismuth has to get over, in a sense. Well, they noticed something interesting. If you just change the surface area, the eukaryotic version can be done by calculating with a large surface area, about the volume of a eukaryotic cell. Remember, bacteria are much smaller. Bacteria look like mitochondria, right? So they're about, they're about 1/100th, 1/1000th the volume of a eukaryotic cell. And so if you have the same volume of bacterial cells, they'll have a much higher surface area. And it turns out that they calculated what the difference is. And all of the difference between eukaryotic cells and bacterial cells could be explained by the fact, not that the bacteria are missing some kind of complex system. It comes down to the fact that the bacteria are smaller. And because they're smaller, they have a higher surface area to volume ratio. And this allows more bismuth to get in because there's more fence for them to hop. The bismuth is sort of pressing on the surface area. So in a sense, they have the same kinetics, different surface area. But this is really good news, because if you think about it, could a bacterium evolve? The only way to get around bismuth is not to evolve a fancy new system to eject it, but to evolve a larger size. And bacteria have a lot of constraints on their size. It's very hard for them to evolve a larger size. In fact, you could argue that it requires, like, endosymbiosing a mitochondrion or evolving new lipids to allow you to have a more flexible membrane like cholesterol. Anyways, all the events from the later half of the book that allowed eukaryotic cells to get this big are what the bacteria would have to do to become bismuth resistant. So in other words, this tells me that I'm not that worried about bismuth. You know, you don't have to worry about taking Pepto-bismol like you do an antibiotic. You can't worry that the bacteria are going to develop immunity to it. By the way, there's actually some exceptions to that statement. They could do like biofilms. They could find ways to hide from it. They could actually increase their surface area by working together. But that's also hard to do. And so this means that fundamentally speaking, at least, Pepto-bismol is still good to use. Right. I would suggest that probably it would have some kind of relationship to the toxicity because it will eventually get into your cells. If you're like drinking a bottle a day, yeah, I have to imagine you'd have some residual bismuth that would be getting into your own cells just a lot slower. But yeah, that's the main thing. The factor right here is dependent on surface area. And it's 2/3 over P, where P is the surface area that is exposed. Different kinetics, different drug action. And that is the data talk for that story. Now your turn is to do it yourself. And so this is why we have a 12-minute presentation assigned. Oh, you know what? I will keep recording this because I'm sure Harleen has questions about this. So I want to make sure that I say what it is. I want you to pick an element. And by the way, you can tell me today which element you want. The good news is you've got about 20 to choose from. Any element that's prominent in the book that had a prominent role in natural history. So start with the index. Look at, be sure to think about geology, chemistry, and biology. Different elements will have different proportions of uses, but it'd be nice to mention something in each area if you can. And I posted Data Talk 7 to 9 slides, by the way. I put those on because there's a lot of small figures and tables that have to do with each element going through. But if you look that up and you see what shapes it likes to bind, what functions it likes to do, what enzymes it's used in, that will be a lot of, that will give you real headway on doing a good talk about the chemistry of how it works in biology. So my one thing is, just like what I did today, I gave you 2 peer-reviewed original research papers and I explained them. I'd like you to do the same thing. You don't have to explain them in as much depth as I did because you only do have 12 minutes. But I want you to go, the more depth that you go into to explain how the element works and how they know how the element works, do that, go into that in some P chemical detail. Mention some concepts that have to do with some chapters from Atkins, okay? Tell us about how they're used in the present. Tell us how they could be used in the future. Tell us how they were used in the past. Any tense is open to you. The main thing is, I do want you to sort of recapitulate how that element was used in the past, the way it was used in A World from Dust, okay? All right, any questions about that?